Hello, everyone, and welcome to today's graph reading group,
where Zian presents his paper where he makes the point or argues for distance matrices being enough to learn on molecular graphs.
Okay, yeah. First, thank you, Hannes, for inviting me to give this presentation. And my name is Zian Li. I'm the incoming PhD student of Peking University, and my my research interests include geometric deep learning and graph neural networks. And the paper I bring today is our recent work on geometric deep learning. Its name is distance matrix enough for geometric deep learning, and it aims to answer a basic question, which is what is the potential of the models that use the most basic geometric feature, the invariant feature distance as input, and can we design models based on distance to achieve completeness and universality? So the authors include me, Xiyuan Wang, Yinan Huang, and Professor Muhan Zhang, and the work is done in Peking University. So let's begin. And the first is the overview of my presentation. We will first do some introduction and introduce our background, and we will then rethink the incompleteness of vanilla DisGNN, a very classical family of models which take bit distance as input. And then we will propose k-DisGNNs is a universal and complete framework geometric models. And then we will show the theoretical analysis of k-DisGNNs from three perspectives, including its ability to extract high-order geometric information and its ability to unify invariant geometric models. And the final part is completeness and universality. We will then evaluate our models in experiments, and the benchmarks include the MD17, the revised MD17, and QM9, and we will do some other experiments to show the effectiveness of our model designs. And we will then do some discussion of our presentation of our work. We will show the limitations and some promising directions of our work. And then we will do some conclusions and summarize our contribution. So let's continue. The first is introduction. And as we all know, lots of real-world tasks are relevant to learning the geometric structure of a given graph. For example, molecular dynamic simulations, physical simulations, drug designing, and other, for example, protein structure predictions. And usually in this text, we usually need to deal with graphs which are embedded in 3D Euclidean space. And in the graphs, each node is attached with its 3D point coordinates, in addition to their other invariant features, for example, atomic numbers. And we usually call these graphs as geometric graphs. And I assume the audience in our reading group are already very familiar with the concept of invariance and equivariance, so I will just skip this. It's important to know that we need to assure the invariance and equivariance for better data efficiency and better generalization. So in the past few years, there are many equivariant neural networks designed to adapt to the variation of coordinates under these group actions. For example, SO3, E3, and O3 groups. These works include the works using SO3 irreducible representation, for example, TFN, and lots of the following works. However, because they use the group theory and lots of other mathematical knowledge, so they can kind of lack of compressibility, and also their universality can hardly be guaranteed because they usually need the intermediate representation to be very high order to achieve the real completeness. And the second kind of models, they use first order equivariant representations, and we also call these as vectors, for example, GNN and other works. However, because they use low dimensional representations, their universality can hardly be ensured. And finally, there are other models use high-order invariant geometric features, for example, DEMNet and GEMNet. These models design and incorporate the high-order geometric information into their message passing framework. For example, DEMNet design and use angle information, and GEMNet use dihedral angle information. However, these models can they heavily rely on handcrafts, and they can be inflexible when dealing with different real-world tasks. So, as we can see, most of the limitations of the previous work, they are brought by one thing, that is coordinates, because as a kind of equivariant feature, coordinates can vary very dramatically under E3 transformation, and it can be redundant when we want to capture the geometric structure information. So how about we change a perspective and see geometric graphs in another form? So corresponding to geometric graphs are distance graphs, which we define as complete weighted graphs with Euclidean distance as edge weight. And in the figure, we show the transformation from geometric graphs to distance graphs. In distance graph, there is no 3D coordinates. So we show some advantages of distance graphs. First, it is naturally invariant under E3 transformation, because so models designed based on distance information is also naturally invariant models. And it can also be very easily to be utilized by most GNNs, because these GNNs can just regard this distance as a kind of edge weight and incorporate it into the message passing framework of them. And it's important to show they have strong inductive bias, because distance, the value of distance itself, can model the pairwise relationship or interaction of different nodes. So yeah, and we show the most important property of distance graphs is that distance graph is complete, because which is two geometric graphs are equivalent under E3 transformation and permutation if and only if two distance graphs are isomorphic. So you can, as we can see, distance graph provide another way which does not refer to a canonical coordinate system, but it can completely represent the geometric structure. So it urges us to fully exploit the potential of models which take only distance graph as input. So this is also the main aim of our paper. And the first part of our paper, the first contribution is that we showed the incompleteness of vanilla DisGNN in another perspective. First of all, what is vanilla DisGNN? We define vanilla DisGNN as the age-enhanced version of message passing neural networks. They take distance graphs as the input, and in the left equation, you can see it is the message passing paradigm of MPNN. It updates node labels based on itself and its neighbor's label. And you can see the vanilla DisGNN's paradigm in the right equation. It just incorporates the edge weight or the distance itself into the message passing framework. And as we all know, there is a famous work named SureNight. It is just a kind of vanilla DisGNN, and in that paper, it calls this as continuous convolution. So actually, in a recent paper, they demonstrated that vanilla DisGNN is not enough for capturing complex geometric structure, or they are not complete, they are incomplete. They constructed pairs of geometric graphs. These graphs are different. They are not the same under E3 transformation, but they cannot be distinguished by vanilla DisGNN. So we can see vanilla DisGNN has some inherent limitation. But however, the counterexamples constructed by this work cannot provide much intuition on the inherent limitation of vanilla DisGNN, because these counterexamples are just very well designed, and they do not say, for example, what exactly kind of graphs cannot be distinguished by vanilla DisGN, and what exactly the structure cannot be captured by them. And it is the first contribution of our work that we showed vanilla DisGN cannot distinguish lots of symmetric structures. So they have the inherent limitation of capturing symmetric configurations. We do this by constructing 3 kinds of counterexamples, and the first kind is some isolated counterexamples sampled from regular polyhedrons. And there are some examples, and you can see in the left figure, there are 2 geometric graphs sampled from regular icosahedron, and there is a ring in the left and 2 triangles in the right. You can see they are very different. They are completely different, but they cannot be distinguished by vanilla DisGN. And in the right, there are also, for example, there is a ring in the left and 2 pentangles in the right. So they are very symmetric and cannot be distinguished. However, the counterexamples showed because they are sampled, so there are only finite numbers of counterexamples. And in the second counterexample, we show a small family of counterexamples. They can be transformed in 1 dimension, so they actually have infinite number of counterexamples. And we do this by combining different regular polyhedrons, and you can see in the right there are 2 cubes, and in the left there is 1 cube and 1 octahedron. They are combined, and we do not limit the relative scale of the 2 polyhedrons. They can scale arbitrarily, so the number is infinite. But we see this as a small family because they can only be transformed in 1 dimension. And in the final we proposed a method to construct arbitrary kind of counterexample, meaning that we gave a very large family of symmetric counterexamples. We do this by you can take any one of the isolated counterexample we proposed in the first can, and it is shown as this, and we call this as the original version, and you can get the complementary version because we take the nodes where we didn't sample, and you get the all version because we take all the nodes on the polyhedron. And for each of the isolated counterexample, we get 3 versions, and we can do some arbitrary combination of the 3 versions to get a new pair of geometric graphs. And we proved that this pair of geometric graphs is still a counterexample. So here we mean the arbitrary combination. We mean we can get arbitrary number of the graphs, and we can get arbitrary version, and we can get arbitrary size. So it's really a big family. Oh, I'm sorry, just. Oh, I'm sorry, I just connected to my AirPods. Oh, it's okay now. And it's worth noting that it's really challenging to construct the counterexamples because our distance graphs must correspond to real 3D structures. So you cannot causally denote, you cannot causally give a distance matrix and say it's a 3D structures distance matrix. It's not possible. So actually it's largely reduced the potential distance graph space. So it's very challenging compared to those counterexamples in the traditional settings, for example, the topological graphs. And to summarize, our counterexamples showed the inherent limitation of vanilla DisGN to capture symmetric configurations. This is important because symmetric structures is very commonly seen in real-life graphs. For example, this is the benzene, and there are 2 rings which are very symmetric, and this is aspirin. It has a substructure where is benzene and 2 rings. So the inherent limitation to capture these symmetric structures rarely limit the performance of vanilla DisGN in real-world tasks. So it can somehow explain the better performance of short-night in real-world tasks. Oh, I see some question. Okay. And given these limitations, we proposed k-DisGNNs, which are actually complete and universal geometric models. First, k-DisGNNs are inspired by K and KFWL measures, and they include three versions of k-DisGN, KF, and ke-DisGN. And note that our works are different from previous work because, for example, PPGN and k-GNN, because our k-DisGN take only distance graph as input, and they aim at learning the rich geometric information contained in it. So given a k-tuple, our k-DisGN first initializes its representation according to its node level invariant features and its ordered distance matrix. It's very important because the distance matrix contains all the geometric information which is needed in the message passing framework. And the paradigm is shown here. And then it iteratively updates the representation and output the global representation by pulling all the tuples representations. So let's focus on the interaction block or the update block. Also, I assume the audience in our reading group are very familiar with the K and KFWL, so I will skip this part because K and KF DisGN just update geometric representations by mimicking K and KFWL. And it's worth noting that k-DisGN cannot capture the relationship between a tuple and its neighbor, which is very important. Let's see the graph in the right. When aggregating the three brown tuple, the three blue tuple cannot be aware of the red edge relation. It's important because, for example, in physical systems, a tuple W far from V should have much less influence on V than another tuple W prime near V. So given this limitation, we propose ke-DisGN, which are models that can capture the relationship between self-tuple and neighbor tuples. We first designed the edge representation by feeding the distance or the edge weights and the tuple related to edge IG to the to MLP to get the edge representation. And then we design the new aggregating schema by incorporating the edge representation into the neighbor tuples. And that's all about the framework of k-DisGN. And in the following parts, we will show theoretically and in experiments the performance of our models. So first, we will show their high theoretical performance. The first perspective is their ability to extract high-order geometric information. Note that this part is more intuitive and is very easy to understand and can help us better understand the geometric learning ability of k-DisGN. First, we will show what is k-order geometric information. We define this as all the E3 invariant geometric features which can be calculated from k-nodes coordinates. For example, we show 2-order, 3-order, and 4-order geometric information in the left graph. They are distance, an angle, and dihedral angle, respectively. And in the right graph, we show some other possible 3-order geometric informations, including the vertical line, the middle line, and the area of a triangle. Because as we can see, the high-order geometric information include, but is not limited to those commonly seen geometric informations, for example, distances or angles. So, and we first note our k-DisGN can capture at least k-order geometric information. This is actually very obvious because they initialize tuples according to the ordered k-size distance matrix. And as we shown in previous slides, these matrices can contain all the geometric information within the k-tuple, and so they can capture this information. And then we show that ke and kf DisGN can capture actually k+1 order geometric information. Because ke and kf DisGN can somehow reconstruct all the k+1 tuples from its input. Because, for example, ke DisGN can capture the relation between 3 tuple and its neighbors, so it can reconstruct the 4 tuple, and kf DisGN can just learn all the 3 tuples within 4 tuples, so it can also reconstruct it. So they can capture all the k+1 order geometric information. And a natural question is, what can they do with the ability to learn high order geometric information? And we show that they can be strictly more powerful than vanilla DisGN. And this is an example. It's an example we constructed in previous slides. It cannot be distinguished by vanilla DisGN because they are very symmetric, and the ring and triangles cannot be captured by them. And we show that they can be distinguished by actually 3 or 2E, 2F DisGN, because they can count the number of small equilateral triangles, and there is no these triangles, and there is 2 triangles in the right, so they can distinguish them. This is because the triangle is just a kind of 3 order geometric information, so they can capture it by 3 or 2E, 2F DisGN. So yeah, as we said, this part is more intuitive. And in the second part, we show our k-DisGN can unify invariant geometric models. First of all, let's introduce some models which are invariant geometric models by incorporating high order geometric information. The first is DisGNNs. DisGNNs is a very classical model which explicitly incorporates angle information into its message passing framework. And you can see the angle information here. It calls this as the directional message passing. And furtherly, DisGNNs explicitly incorporates both angle and dihedral angle information into its message passing. And you can see dihedral angle information here, and it calls this as a 2-half directional message passing. Note that they incorporate by explicitly design the higher order geometric information. And in the following slides, we show these models are just very special cases of our k-DisGNNs, because our models can implicitly learn arbitrary k-order geometric information. So we gave 2 propositions here, and the first proposition shows our 2E and 2F DisGN can implement DisGNNs. And the key insight for the proposition is that angle is just one kind of 3 geometric information which can be learned by our 2E and 2F DisGN. And the second proposition showed that 3E and 3F DisGN can actually implement DisGNNs. And the key insight is that dihedral angle is just one kind of 4-order geometric information. And please note that although both our models and the DisGNNs can learn this k-order information, our models have the ability to learn arbitrary k-order geometric information, including, but it's not limited to angle or dihedral angle. So they can be more flexible when dealing with different real-world tasks. And in the following slide, we show the completeness and the universality of our models, and it's the final perspective, and it's the most important. Actually, as we can validate all the counterexamples we constructed in the first part of our paper can be distinguished by 2E or 2F DisGN and 3 DisGN. So a natural question is, are they powerful enough to distinguish all geometric graphs with a finite k? Or can we can ask with a small k? So in the following slides, we will show some theorems which give the completeness and universality of our models. And the first theorem, we will show 1 round for DisGN and 2 round 3E, 3F DisGNs properties. Here, round we mean the iteration number of message passing. And they have the following properties. And the first is they are complete, meaning that there exists some parameter z0 such that our model can distinguish all non-congruent geometric graphs. And here, non-congruent means the two graphs are not geometrically isomorphic. They are not the same under E3 transformation. And the second property is they are universal for scalars, meaning that they are m theta is a universal function approximator for continuous and E3 and permutation invariant functions over geometric graphs. And the key insight for the two properties is that actually 1 point can be determined to at most 2 possible positions if we give the distances of them from 3 affine independent points, as shown in the right figure. If you give the distance from the red node to the 3 green nodes, you can actually get its positions to its 2 possible positions. And actually, we can eliminate 1 fake position in some way, and we can maintain the real position and reconstruct the whole geometry from the output of M in a step-by-step manner. So it's worth noting that it's very different from what we have seen in traditional graph representation learning fields, because in that fields, where we do not consider 3D information, you must need KWL, the K in KWL to be very high, to be infinite to solve the graph isomorphic problem. And the K inside they are different is that there is some very strong constraints in geometric settings, which is actually you can understand this as the this sentence, because if we give the distances from 1 point to 3 different points, and we can get its positions. And that's the universality for scalars. And as we cited in previous slides, by combining the conclusion from the paper called Scalars Are Universal, we can actually use our scalar model to construct equivariant models. So we first denote the node representation because in KWL or k-DisGNNs, there are tuple representations and there is no node representation. So we first define HM as the node representation by pulling all the tuple representation where the first index is M, and we get it. And then we can construct the vector functions, and we have the following properties. This is a universal function approximator for continuous and O3 and O3 equivariant and translation and permutation invariant functions over geometric graphs. So the key insight of this part is actually HM is a universal node level.
Sorry, Zian, your audio just... Is it only on my side, Dom?
No, the audio has cut also on my side.
Zian?
Zian, now the video has cut as well.
Yeah. Let's hope for the AirPods.
He seems to be continuing the presentation.
Yeah, let's hope for the AirPods, and let's also raise our hands and try to get his attention in another way. Yeah. What else can we do?
I'm sorry.
Hello, Zian. Can we hear you again?
Yeah, I can hear you.
Okay, are you good? And then I think everything works again. Do you know what the issue was?
I'm sorry, I just maybe my computer connected to my AirPods just before.
Okay, good. But then where were we before we stopped hearing each other? Tom, do you know?
It was last slide, I think.
Yeah.
No? Or 1 minute ago. Like if you can go back 1 minute in the presentation. The first
like if
the
you
first
just
point here.
explain the first point here again. No, next slide. You just explain.
It's here.
And now I'm confused where we are.
Okay, at the beginning, the last slide. Okay.
No. I think two slides from here.
Yeah, one more slide. Previous slide.
I'm sorry, is it here?
Can you go to the previous slide again?
This?
No, not that one, the next one.
Next one is this?
Yeah.
Yeah, okay. I'm sorry. I just disconnected my AirPods. Oh, let's start here. Okay. Yeah, as we said, lots of models, they improve their geometric learning ability by explicitly incorporating the handcrafted high-order geometric information into their massive passing framework. And in the next slide, we will show these models are just very special cases of our k-DisGNN because our models can implicitly learn arbitrary k-order geometric information. So we give the first proposition. We heard this, but I'm not looking here. I'm sorry, can you hear me?
Yes, we can. Maybe I'm wrong, but I think that this slide was okay.
Yeah. Oh, so the first proposition is we show that 2E and 2F DisGNN can implement DisGNNs. And the key insight for this is angle is just one kind of three-order geometric information. And we then gave the second proposition, and we show 3E and 3F DisGNN can implement DisGNNs because the dihedral angle is just one kind of four-order geometric information. And it's worth noting that although our models and you see DisGNN and DisGNN can all learn the angle or dihedral angle information, our models have the ability to learn arbitrary k-order geometric information. So our models can be more flexible for different real-world tasks, and it can perform good in a data-driven manner. So that's the first two perspectives of the theoretical expressiveness of our models, and we will show the most important part of our models, namely the completeness and universality of k-DisGNNs. And first, actually, as we can validate, all the counterexamples we constructed can be distinguished by 2E, 2F, or 3E DisGNN. So it's a natural question to ask, are k-DisGNN powerful enough to distinguish all geometric graphs with a finite and small k? So in the following theorems, we will show they can, and they can do it with a very small k. The first theorem, we show that let M theta be the models in the set, including one round for DisGNN and two round 3E, 3F DisGNN. Here we mean, here the round we mean it is a number of the message passing iterations of DisGNNs. So they have the following properties. The first is they're complete. This meaning that there exists some parameter theta 0 such that M theta 0 can distinguish all non-congruent geometric graphs. And here non-congruent we mean they are non geometrically isomorphic meaning that they are not the same under E3 transformation. And the second property is they are universal for scalars, meaning that m theta is a universal function approximator for continuous E3 and permutation invariant functions over geometric graphs. And the key insight for this is actually in geometric setting, we can determine one point's coordinates to at most 2 possible positions if we are given the distances from 3 affine independent points. You can see the red figure. If we know the distances from the red node to the 3 green nodes, we can actually determine its positions to these 2 possible positions. And actually, we can eliminate one fake position and maintain one real position in some way, and we can then reconstruct the whole geometry from the output of M in a step-by-step manner. It's worth noting that this is very different from the traditional graph in representation learning field. Because in that field, you know, if you want to solve the geometry, the graph isomorphic problem, you need the k in KWL to be infinite to solve this. But we prove that in geometric setting, you only need the order k to be 2 or 3. Yeah. And as we said in previous slides, if we can use our scalar model to construct equivariant models by using the conclusions given by the paper, named scalars are universal. So let's first denote HM as the node M's representation, which are produced by M, and it is calculated by pulling all the tuple representations where the first index is M, and you can use this node level representation to construct the equivariant function, which is proved to be a universal function approximator for all the continuous and all 3 equivariant and translation and permutation invariant functions over geometric graphs. So they have the property that is universality for vectors. And the key insight for this is actually this HM is a universal node level representation, and we can use this to approximate any linear combination coefficient for coordinates. And as we shown, we can use the k, where k is larger than 3, to have these properties. And in the following theorem, we show that k can be lowered to only 2. And this is inspired by a concurrent work by Daly Rose, which also investigates the completeness of geometric KWL on distance graphs. And in construct to our approach of using only one tuple's final representation to reconstruct the geometry, they actually leveraged all the tuple's final representations. And we can extend their conclusions to k-DisGNN and get the following theorem, which is the completeness and universality for scalars stated in theorem 1 also hold for these models, including 3 round 2E or 2F DisGNN and 1 round 3E and 3F DisGNN. And note that because we use lower order and favor rounds here, the expressiveness of a single node representation, which we defined in the previous slide, HM, is universality may be limited. So we may not guarantee the universality for vectors stated in theorem 1. And these are all the, and to summarize, we can achieve universality for scalars, and we can achieve completeness when k is larger than 2, and we can achieve the universality for vectors when k is larger than 3. And then we will evaluate our model's performance in some experiments, and in this part we will focus on several questions. And the first is, does our models 2 and 3 and E and F-variant DisGN can they outperform their counterparts in experiments? And here counterparts we mean is for 2 order is DisGNNs and for 3 order is GNNs, because we showed in the theoretical part 2 order can implement DisGNNs and 3 order can implement GNNs. So we want to see their experimental performance. And the second question is, as universal models for scalars, when k is larger than 2, do k-DisGNNs also have very good experimental performance? And actually, in this question, we want to compare our models to other models, including those SOTA models, and see if they can achieve the, for example, the SOTA performance. And in the third question, we want to see does incorporating the well-designed age representation in our k-DisGNN can result in the improved performance. Because as we can see, when we add age representation or age relation into k-DisGNN, it is theoretically better, and we want to see does it add any entity bias, or does it improve our experimental performance? And we do some experiments on the MD17 benchmark, and in MD17 benchmark there as the node coordinates of every node is given, and we also know the atomic number of every atom, and the task is to predict the energy of the molecule, and we want to also to predict the force on each atom. And we show the results in the table. The best result is in bold, and the second best is in underline, and we will color the cell if k-DisGN can outperform their counterparts. And we can get some conclusions from this table, including the first is we can see our 2F and 3E DisGN can outperform their counterpart on all the targets and 6 out of 8 targets respectively, and their improvement are 40% and 12% on average. And the second conclusion is our models can achieve the best performance on half of the targets and the second best otherwise. And we can see our models can outperform the best baselines, GNLF and TorchMD, by 10% and 12% respectively. So they can really, they have really good experimental performance. And we also conducted experiments on the revised MD17, which have better data quality than the original MD17, because they use better calculation methods, and so they have lower data noise. So this will better reflect our model's performance. And in this part, we mainly compare our 2F DisGN to the SOTA models, including MIS and Allegro. Note that these two models both use very complex SO3 irreducible representations, so the results really means a lot. And the first we can get from the table is our 2F DisGN can achieve half of the best performance and 4 out of 20 second best. So it again gets a wide range of SOTA results. And this can, as we can see, this further reveals the potential of our distance-based model and our data-driven model to learn the high-order geometric patterns. So we also conducted our experiments on QM9, which contains small molecules with various kinds and sizes. And in this data set, our goal is to learn more molecular scalar properties, not limited to the energy of the molecule. So we mainly compare our model to DisGNNs, and we can get the following conclusions. We can see 2F DisGN can outperform its counterparts on 9 out of 12 targets, and especially on these 2 targets where they get the improvement of 60% and 90%. So these experiments really well answered the first 2 questions. And then we want to test the effectiveness of our well-designed edge representation. And we will design two kinds of models, including the small e variant, which adds only edge weights or distance, and they do not add the tuple representation. And the full variant or the big E variant, they add both the edge weights and the tuple representation. And we compare two DisGNN, two small e DisGNN and two big E DisGNN, and we can get several conclusions. And as we can see, two small e and two big E DisGNN can outperform two DisGNN by a very large margin. This validates the importance of capturing relationship between tuples. And further, we can see two big E DisGNN can outperform two small e DisGNN on 12 out of 16 targets, which further verifying the importance of capturing full edge features, both edge weights and tuple representations. So let's do some discussion. And as we can see, k-DisGNN can achieve very high performance, both in theory and experiments. They can do this by extracting high-order geometric information from the most basic geometric and invariant feature distance. And we showed that distance graphs have very high potential for geometric deep learning. And we created the new opportunities for graph deep learning, geometric deep learning, which is we can apply expressive GNNs, which are originally designed in traditional GRL, onto distance graphs, and we can obtain very high theoretical and experimental performances. Let's show some limitations of our work. The first is, as we can see, the theoretical guarantee is still under the assumption that the distance graph is complete, which can be very intractable for large graphs, for example, proteins, because in these graphs, there may be thousands or millions of nodes, and we cannot easily store or process the complete distance graphs. And the second limitation is even for our 2E and 2F DisGNN, they are universal models for scalars. This will lead to the quadratic space complexity and the cube time complexity. So we will give some possible solutions. The first is we can use appropriate cutoff. Here, the cutoff, the appropriate, we mean it can further preserve the completeness of the distance matrix in local clusters. This is for their theoretical expressiveness, and we can cut long dependencies to improve their efficiency. And we can actually apply other sparse but expressive GNNs in traditional graph representation learning field, for example, subgraph GNNs and so on. And let's summarize the contributions of our work again. We first constructed more counterexamples which can reveal the limitation of vanilla DisGNN in capturing symmetric structures. And then we proposed k-DisGNNs, their theoretical, complete, and universal geometric models over distance graphs. And we showed they are complete and universal for scalars when k is larger than 2, and they are universal for vectors when k is larger than 3. And we get a wide range of SOTA experimental results on both original and revised MD17. And finally, we created new opportunities for graph geometric deep learning, which is we can design powerful geometric models by transferring knowledge from traditional graph representation learning fields. And here, traditional, we mean there is no 3D information, there is no node coordinates or distances and so on. They process the topological graphs. And that's all for today's presentation, and feel free to ask questions.
Very nice, very nice. Thank you. We do indeed have some questions. Yeah, but first, pretty cool to see this work. And then from Francesco, how efficient is this representation? Number of parameters, for example. How does this model generalize?
Okay. Actually, this representation we call as distance graph is as we said, it is its limitation is it can be intractable. But if we use it for small molecules, we do not need very many number of parameters. For example, in our 2F DisGNN, there is only about 10 millions of or 5 millions of parameters and so on. Yeah.
Okay, then do we have any other questions from people in the audience, or Francesco, do you have any more questions?
Yes, curiosity about how the model generalized, no? Because I can see that can distinguish very well, let's say classify, but maybe it's not easy the generalization, even if the model performance is very high. Yes, if Zian has an intuition on how the model generalize.
Yeah, thanks for the question. And can I ask, what do you exactly mean by generalizes or this model generalizing?
Yes, so if you see an example which is close, then you know. If you use the nearest neighbor, you know that you using the feature, you know that there are example close by, so you use that example to predict. But as I see, it seems that you're considering the neighbor, a lot of neighbors, and so this will change a lot, even by changing, by moving just slightly, let's say. So that's my question. If you have an intuition how the model can generalize. No?
Yeah, actually, as for now, we only consider the complete graphs, and we do not use any cutoff. But we believe it can, for example, as we said in the final slides, if you add appropriate cutoff, it can actually, I mean, it will still have good experimental performance, and it will not suffer much experimental loss. Performance loss. And I don't know if I
understand. Thank you.
Yeah, thanks for the question.
Okay, very nice. Then, Zian, do you have any last comments that you want to say, or any last statements or takeaways that you really want us to have?
Yeah, yeah, maybe I will again note that as we showed, distance graph is very important, is very potential because it have very strong inductive bias. So maybe we can it is another way to which will achieve completeness and universality compared to those equivariant models. So maybe we can design other powerful geometric models on this and work on this kind of representation. And actually, our recent work is still based on distance graphs, and our experimental results are very promising. And yeah, that's all.
Okay, then we have one last question by Hauran. What is the computation complexity for k-DisGNN? And also like compared to DimeNet, GemNet, and maybe you can talk a little bit about how in practice the runtime is.
Yeah, thanks for the question. And the complexity of k-DisGNN, for example, for KF and ke-DisGNN, they use the k exponential power of n, k+1 exponential power of n for the time complexity. And if you compare this to DimeNet and GemNet, they are the same because both of them need to process, for example, 3 tuples or 4 tuples, because GemNet use 2 hop, so their theoretical complexity are the same. but as we showed in the table, our models can perform much better than those models. Yeah, and I see Xiaojin's question.
Yeah, about M22, and it has larger molecules, right? And maybe also less noisy values.
Yeah, actually, we haven't done conducted experiments on MD22, but we will do this afterwards. And for large molecules, as we said before, as we said in the limitation part, it is actually intractable because we needed the complete distance graph to achieve high theoretical performance. But we can, as we said in the some possible solutions, we can use sparse but expressive GNNs such as subgraph GNN. So maybe we will focus on this by using subgraph GNNs and test it on large molecules, and we will report these results afterwards. Yeah. Can they deal with long-range interaction well? Yeah, that's a good question. But actually, for now, for this paper, we only conduct experiments on small molecules, and we will do and we will conduct the experiments later. Yeah, thank you for the question.
Yeah, I guess now the questions are coming in. How important is the design of the function that extracts the initial invariant features? I think I read in the paper that an MLP did not work so well.
Okay, how important is it? Yeah. I understand your question. Because we said in our paper, we use a special design. I will show the slide. Sorry. Oh, here. We just gave the form of our function, and our realization is we will pass these different elements into different MLP, and we will multiply them and get the H0. So actually, in experimental, in theory, they are the same because they can both learn the injective. They are both injective functions, and they can learn all the geometric information. But in the set of experimental, our design is better. Yeah. I don't think it's very important because maybe it's just it just provides more inductive bias. Yeah.
Okay, and then Dom is writing the question in the chat.
Yeah, I can say it out loud. I know, like, here you compare a lot to DimeNet and GemNet, and we know DimeNet uses angles and GemNet uses dihedral angles. And I would like to know, like, is there some similar notions or interpretable notions that are learned by your current model? For example, have you looked at, like, how the embedding changes with angles or something like that?
Yeah, thanks for the question. And we believe our models can, we believe they didn't learn exactly the angles or the dihedral angles. They actually learn, they actually process and update high order tensors. So maybe just some abstract high order geometric information, and there may not be so many similar notions. They are just k-order geometric informations. Yeah, I don't know if I.
Yeah. So how do you know that your model did not learn angles and dihedral angles?
Yeah, just as showed in this slide. Yeah, they just process I mean k order distance matrix. So yeah, we didn't test if they learned the angles or dihedral angles, but they just perform well in experiments. Yeah, they just process high order tensors. Yeah.
And do you think that pre-training your model to learn angles and dihedral angles, or having that as a another task in a multitask setting, could help like regularize the network?
Yeah, I believe it will help. And actually, pre-training our models is just our previous thought. So maybe they will just learn how to better extract some exact k-order information. Yeah, actually, I also think now if you only use a very small number of training data points, our models can have relatively worse generalization power. So I believe pre-training or other methods will help them to learn k-order information. Yeah, that's right.
Okay, nice. And yeah, so for molecules, if I'm not mistaken, like I don't think there's any reason to go more than 3K in terms of order. But like, do you have examples of like structures in mind where you need K to be like a larger number, like 5, 10, something like that, in order to distinguish everything?
I'm sorry, can you repeat it?
So do you have examples where like you need the K order to be where K is very large, like very large, like 5, 6, 7, and not just like 2 or 3, like it's the case with the small molecules?
Yeah, actually in theoretical, it does not need to be very high as we showed in our theorem. It only needs to be 2 to achieve completeness is not relevant to the size of molecules. So if you always fit them into the complete distance matrix, they can always distinguish because they can reconstruct the whole geometry structure from the output. So can I understand your question? Are you just want to ask?
Yeah, so you're saying that your model with K equal 3 is complete?
Yeah.
Right?
Yeah.
Okay. And so this is complete in 3D. Do you have any idea if like your model generalizes to 4-dimensional geometries or 5-dimensional geometries?
Oh yeah. That's very natural because we believe, for example, we show 2 order K equals 2 is enough for 3D, and it's very natural to derive the congruence that, for example, 3 order is enough for 4D, and for the proof method is very similar.
Okay. Yeah, thank you.
Thanks for the question. And for Xiyuan, yeah, I will can share the slide for future reference. Yeah, I think I.
Okay. And also we had a question about recording. Yes, the recording will be made available. So Zian here argued for the fact that we only need to look at distance matrices when we want to learn something about molecules in 3D space. I think this is maybe the case for some certain applications that we looked at and for the results that we see in the paper, but I'm a bit wary for generalizing this to everything. And yeah, maybe we can have a look at other papers for insights into that. And if you want to do that with us together, then join us in the reading group next time around with all the information in the description, where you can also propose your papers of wishes that we should have here. See you.